Hello everyone, here we are presenting our work titled Data Augmentation via Latent Diffusion for Saliency Prediction. Saliency prediction aims to computationally detect the regions in an image that gather an observer's attention. Existing models are constrained by the limited diversity and quantity of labeled data. In this graph, we show commonly used saliency datasets in dashed bars alongside datasets for other computer vision tasks. Notice the significant difference, especially with Lion 5B, highlighting the scarcity of labeled data for saliency. In the general computer vision context, limited access to data is typically overcome via data augmentation. For tasks like image classification and object detection, classical augmentation techniques such as shearing, cropping, rotation, flipping, and blurring are widely used. These transformations preserve the labels in those tasks. What if we use existing augmentation methods for saliency prediction? We see an example here. Under a cropping transformation, we can see that the player is still a player, so its class doesn't change. Consequently, its label is preserved under the classification task. However, this transformation affects saliency since it is highly scene-dependent. If only one man is present, our attention is focused on him. However, if we have the man and the text, then our attention is divided between these two regions. Adding more interesting regions will complicate the attention distribution. As you can see in the middle example, the text seems to be more important than the player, but in the original image, the player is more salient than the text. Therefore, it is difficult to predict how the labels will change under a cropping transformation in saliency prediction, making it infeasible to generate augmented image label pairs in this way. This brings us back to the core challenge of saliency estimation. Instead of looking for a strictly label-preserving transformation, can we change saliency in a predictable way? Yes, we can, and in this work we build upon this idea. We select a region and increase the saliency over that region. The final saliency of this edited region should be higher than the original one. Therefore, this is a transformation for saliency estimation, where the direction of change in saliency is known. We use a special loss function to capture the saliency change, which we will explain shortly. Now, let's introduce our framework. Here is an overview of our model. The top part is a diffusion model. We extract two sets of features, low-level and high-level. Through several readout layers on these features, we force the network to store relevant information. So, the low-level features should contain the information to predict the photometric properties of the selected image patch. Similarly, high-level features should contain the semantics to predict the class of the patch. To augment data, we first use a saliency-guided cross-attention mechanism to localize the region we want to modify. Then, we edit the photometric properties of the image, preserving the complexity and variability of real-world scenes. For more details, we refer the reader to our project website. Here, we show examples of our edits. In the first row, we increase the contrast of the bread. In the second and third rows, we change the brightness of the bus and the color of the chair respectively. We validate that these edits increase human attention over those regions with an eye-tracking study. How do we train the saliency prediction models using our augmentations? Given an image, saliency ground truth, and the target region to edit, we generate the image edits using our augmentation method. Then, we predict saliency for the original and the edited images respectively. Since our edits enhance saliency in the edited regions, we calculate the binary cross-entropy between the saliency predictions of the original and edited images. Specifically, the loss asks, did you increase the saliency prediction over this region after the augmentation? In other words, we penalize the model if it underestimates the saliency of the edited regions. By applying this loss alongside our augmentations, we consistently improve the performance of state-of-the-art saliency prediction models. So, we have introduced our data augmentation method for saliency prediction. This is especially beneficial in the domains where we have limited data. Our data augmentation method is suitable for saliency prediction. consistently improving state-of-the-art models. Lastly, leveraging augmentation features for saliency prediction also yields a better understanding of visual attention patterns. For further details on all the ablations and additional results, please visit our project page. This work was supported in part by the Swiss National Science Foundation via the Synergia grant.